Welcome, Basho Braju. Welcome, Archana. So we'll be starting our session within 2 minutes. Let's wait for others to join. Okay, so I'll share my screen. Good evening, everyone. Hope my voice is loud and clear and my screen is visible. Uh, if you have any questions regarding our previous sessions, you can ask. You can unmute yourself and ask, or you can type in the chat box as usual. Okay, so let's start. I hope people will join in the meantime. So my name is Shudanu Sadhukan. I am teaching assistant under PMRF NPTEL weekly live interactive sessions. I'm a PhD scholar from IIT Bombay, and I welcome you all to the third interactive session of NPTEL course code C39, that is water and wastewater treatment, offered by Dr. Bhanu Prakash Belanki. civil engineering professor and then environmental engineer from the department, from the civil engineering department at IIT Roorkee. So two sessions have been completed so far. Today we are at the third session, right? So I will brief you a bit regarding whatever we discussed till in the last week, especially because the last 20 or 25 minutes or so were in a bit hustle in the last week, right? So I'll just spend let's say 10 or 12 minutes just to quickly go through which I discussed in the last portion of my of the second week. So first I will tell a bit about the economic water scarcity. So which is nothing but the absence of management or infrastructure, proper management or infrastructure to deliver the water from the source to the people who need it. So welcome Krishna Prasad. So I hope if you have attended last lecture, if you have not attended, I'll be hoping that you should watch the recording. If you have any doubt, you can ask the doubt in the next session, or you can ask the doubt in the forum. If you have doubt regarding how to ask questions in the forum, I have already discussed in my previous lecture, previous recordings. So you can also ask, and I can re-explain. Okay, and also how to access the recordings. I hope it is clear to all. Okay, so I am just briefing a bit in whatever was discussed at the last portion of my second weekly interactive session. So first I discussed about economic water scarcity. Then a brief concept about the hydraulic residence time was discussed, which is nothing but the average duration of a particle of water to pass through a phase of hydrological cycle. So one problem was solved uh, to for the better understanding of the concept of HRT. Then we saw the definition of batch reactor, plug flow reactor, and CSTR or mixed flow reactor. Then we saw the design equations or performance equations of various types of reactors. Batch, constant start tank or MFR, and plug flow reactor. Then we derived the equation uh, for first order kinetics in the case of a batch flow system. So if you do the similar mass balance for other order systems also, in case of other continuous flow reactors like PFR, CST or MFR, then the T or time term will be replaced with the T0 or theta term, which is nothing but the space time expressed as reactor volume divided by volumetric flow rate. And this type of equations we will obtain. Then we focused on the first order kinetics only, and based on the first order kinetics, that is for all the three types of reactor, batch, PFR and MFR, we solved one problem at our last class. So I hope the way the problem was solved, it is clear to everyone. So if you have any questions regarding how the problem was solved, then you can re-ask the questions. We just did the mass balance and derived these equations, and these same equations were used to solve the problems, to get the answers. Just you have to put the known values of the equations in the problem, and then you will get the unknown parameter of the from the equation. Okay, so I'm just quickly go through which was discussed at our last session. So if anyone has any doubt regarding understanding of the same, then they can ask. Abhishek has joined, and Kannan, welcome you too. So this was the last thing. That is the third problem, which there was asked regarding MFR. So you just had to utilize the equation, mass balance equation, which is applicable for CSTR or MFR system. And based on the given data in the question, you got the answer. So this was the problem which was solved in our last session. I will ask everyone present in the audience if you have any doubt regarding the solution and how to solve this kind of mass balance problems for different types of reactors for different order systems. If you still have any doubt, then you can ask now. So this is the correct time for you to ask. I can clarify the same for you, or otherwise I'll be going through our today's new problems. Nobody has any question, I guess. I will wait for a minute. To everyone, is it clear how the mass balance problems are solved in our last class for different types of reactors? You just have to, the mass balance equations are solved by integration. So if you don't know integration, you just have to remember the formula. That's all. So this table is basically comes to your aid. So this is the table. These formulas you have to remember. So we solve problem based on the first order kinetics only. Higher order terms you don't have to remember. So zero first and second order is enough, more than enough I would say for you. So if you don't know integration, you just have to remember this table, memorize this table for the solution of the problem. Mainly you will be given problem from zero and first order only. Second order is also rare. And if you just memorize this table, this type of problem will be you will be easy. It will be easy for you to solve this kind of problems. Okay, so we will start our next session today. So there are two forms floated for the feedbacks. So the problem solving sessions recording videos are timely uploaded inside this separate unit called as the problem solving session along with the slides wherever applicable. So this is the link to the recording sheet. So where all the three TAs who are taking the session, their recordings are uploaded. You can access them. And this is the link to the form for feedbacks against the weekly live interactive session. So I will encourage everyone to fill up this also to them who will be watching the recording later. Please fill this form so that we can gauge your expectation regarding regarding the course with which you registered, and also please give your feedback, valuable feedbacks against the regular weekly course contents. So all the three links are provided. So I will encourage everyone to give your feedback. So if you have not given the feedback yet, I will post the all the links in your in your chat box. So I will give you 2 minutes to fill this form also now. So if you have not filled it up, kindly fill it up. So this is the link for the recording session. This is the your uh, recording link. Okay. Then this link is your feedback for live sessions. Please take your time to fill the feedback form. Also, those who will be watching, I think you have received this link. So we highly encourage you to give your feedbacks. And this link is for your course content. Feedback for regular recorded course contents. Those are lectures by Dr. Bhelanki. Okay, so please take your time. If you have not, so you please raise your hand. Archana, Prashant, and Bashav Raju. If you have filled this feedback form, then I will just keep this. Only 3 are there. So just tell me if you have filled this feedback or not. Bashav Raju, have you filled it up? Okay, 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 okay. Okay, then after watching then you can fill it up. And Archana and Krishna Prasad, have you filled the feedback form or skipped any recording or whatever? Okay, okay. If you have not, please take your time to fill it up. Mm, I'll give you 1 minute. After that, I can start. Or later, you can also, if you have not watched the recording, please go and watch the recordings and fill the feedback. So how the sessions are going, if they're too fast or too slow, any improvement is needed. So you can express your thoughts on that, and we will modify our content accordingly. And we also, if you have any queries, we will try to address those queries. Okay, so I will restart. So today's problems is being started with this question. The characteristics of fresh and septic sewage respectively are. So the first few questions are based on sewage. This is an MCQ. The options are alkaline and acidic, acidic and alkaline, both acidic and both alkaline. You just type your answer in the chat box, or you can unmute yourself. Bashobraju is telling both are alkaline. Are you saying, or option A you are saying? Which one you are saying? Fresh or septic sewage both alkaline? Are you saying? Okay, okay. I got it. Others, please go ahead. Don't be shy. This is just for practice. If you have thought something, then you can also express that I have thought it because of this. So your logic is also important. If there is certain logical flaws in that, or if I may be wrong, so then it gets modified in this process. So it is a kind of interactive practice. So if you have the others, what about the other Krishna Prasad and Prashant? Okay, so I'll go with the answer. Uh, yeah, yeah. So basically, pH of fresh sewage is more than 7. The average range is from 7.5 to 9.5, and hence fresh sewage is alkaline in nature. It is true, but pH of septic sewage is less than 7. So whose average range is between 6.5 to 4.5. Basically 4.5 to 6.5, and hence septic sewage is acidic in nature. So why is it so? Anyone else? Anyone would like to answer? It is quite obvious, basically, because the microbes which are present inside the fresh sewage, as it gets treated, so the more acid is generated, basically. So that's why the pH gets lower. It's just like if you have food particles in your teeth, then there are microbes. They will degrade that food particle, right? And acid will generate, and it will degrade the calcium carbonate that is present inside your teeth. The same thing is for this also, because of the microbial activity mainly, and also some other aspects are also there. That's why mainly it gets as it because septic sewage, you see, it is basically in a closed environment, but fresh sewage is not. It is transported like that way. That's why it is generally acidic in nature, and fresh sewage is alkaline. Okay. So that's why this is the basically pH range. You just have to remember the pH range. So that's why you will be able to answer. So more than 7 is basically your alkaline, and if it is less than 7, it is acidic. That's all. pH, I know everybody knows how the pH is calculated. It is the concentration. If you take the concentration of H plus ion that is present inside a liquid, then if you take the minus log of it, that will be your pH. So P, the term small p means minus log. That's all. So now going to the next question. Which one of the following factors doesn't affect the rate of the sewage load? So this is also an MCQ. The options are: option A, rate of the water supply; option B is population growth; option C is infiltration of groundwater; and option D is design of sewer system. I will wait for 2 minutes for you to type the answer in the chat box. A, B, C, D. In this way you can write. Okay, Prashant is telling us C, that is infiltration of groundwater. It doesn't affect the rate of sewage load, you are saying. So I would say that the rate of sewage load where? So basically the tank is basically located, the sewage treatment plant where the sewage is basically loaded, it is your on the ground. So do you really think that infiltration of groundwater won't affect the rate of sewage load? Generally the sewage treatment facility where and the tank where the sewage is stored, it is generally touching the ground. It is not generally designed above the ground. So there are chances of infiltration of groundwater inside the uh, sewage tank. So do you think if there is chances of infiltration of groundwater inside the sewage tank, will it affect the sewage load? What do you think about that? Rate of water supply, Vasubraju is saying. So you see, the amount of water that needs to be treated, that's only basically sewage. The household wastewater that is coming at the water treatment plant, that is basically your sewage. So the household use. So if the supply increases, the household basically the supply actually given based on the demand of the households, right? So if the demands increases, the supply also increases. So if the supply of the waters increases, then the sewage that is getting generated from the household, what do you think about that? Will it change or not? Or if the supply gets decreases, so the wastewater that is coming out of the households, will it change or not? Because the our body is basically, you can assume our body as a steady state, right? And also you can assume the houses to be a steady state. So the water that is going in, that is being supplied into those houses, that the same amount of water is basically coming out, though the water particles are not the exactly the same, but the amount of the water that is going in, the same amount of water more or less coming out of the systems, except there are huge cooling towers for centralized air condition. So in those cases, there will be water losses. Basically, there will be no sewage generation. But all the other cases, basically, rate of the water supply and infiltration of groundwater, both actually your affects the rate of the sewage load. And population growth, what about that? If the population increases, basically the demand also increases. If the population decreases, the demands decreases, as well as supply also decreases. And this affects the rate of the sewage load. So all the first three are factors which affect the rate of the sewage load. The only factor that doesn't affect the rate of the sewage load is the design of the sewer system, because design of the sewer system is done before the sewage comes into the treatment plant. So it is a pre-designed kind of thing. So once it is designed, actually it has no effect on the rate of sewage that is coming from the households to the municipal sewage treatment plant. Right, sewer system means the pipes, big huge pipes or underground sewers through which the sewage is flowing. Sewage is flowing from where to where? From households, mainly from the households to the mainly to the municipal sewage treatment plants. So once the design is done, you can do nothing about it. So basically, during design, some excess factors are considered, right? Let's say 10%, not even 10%, even more. So they have to project the population in that area for the next 20 or 30 years, let's say maybe up to 50 years. So they have to project the population. Accordingly, they have to take the excess design and they have to uh, design the sewer system taking the relaxation factor into consideration. If the if it is under design, then they can again they can then they have to again uh, like uh, dig the roads, and it will hamper the transportation. So it will be a big mess. So that's why design of the sewer system is a kind of pre-design. So after designing, it doesn't affect the rate of the sewage load. Even if the sewage load increases, what will happen? It will create back pressure. So your drains and everything, those will overflow. Right, the thing that happens during your rainy seasons. So as the water increases, sometimes the sewers gets flooded. So it's a example of poor design of the sewer system, because the past rainfall data of that area was not considered during the design of the sewer system. So those things must be considered while the design. But the rate of the flow of the sewage, the design is, the sewer system is designed to handle the rate of the to handle the load of the sewage. So it doesn't affect the rate of sewage flow. Okay, I hope it is clear. So I think nobody answered it correctly. So if anybody has any objection to the answer, they can express their thoughts. Okay, otherwise we will go to the next problem. I hope nobody has any objection. I'll go to the next problem. Next problem is also an MCQ. Non-spherical particles will settle slower than, faster than, equal to, or same as spherical particles. If let's say you are having a tank, a settling tank, and there are uh, you have put wastewater uh, with let's say visible particles, the particles which are visible in our naked eye. So they will you have put that water inside the tank. You are holding that water in the tank so that the particles which are not visible in the water. I discussed the size range of the different particles in my last class. Can anybody say those ranges? So you all have studied those ranges in your madhyamik, that is your 10th level, secondary level, schools level. You have studied those ranges. So if it is between 10 to the power 5 minus 5 and 10 to the power minus 7 meter, generally those are colloid or suspended particles. If the particles is less than that, that is the nano ranges or angstrom ranges, those particles are dissolved in the water. If the particle size is more than 10 to the power 5 minus 5 meter, that is your in your more than microns levels. If it is micron level, then it will basically suspended. If it is more than that, then the particles will be your, it will be not be completely miscible with the water. If you keep the water stationary, if it is not stagnant, if it is flowing, then it will by the help of eddy currents and turbulence, it will be mixed with the water. But if you keep it for settle it for a long time, then the particles which are bigger, they will settle down. So if one particle is settling, there is a concept called as a terminal settling velocity. So if the particles is settling, the equal amount of drag force actually applied it upward. So there is a formula of the drag force. Those of you who had science in your plus 2 level, they will know if D equals to 6 pi eta rb, or 3 pi d, r means 6 pi into that thing goes to with r. So it is your the drag force formula is becomes your 3 pi mu dv, where v is the velocity or the terminal settling velocity of the particle. So the velocity with which the particle is settling, it is balanced. If it is balanced by the drag force, then it becomes the terminal settling velocity. That means the velocity is neither accelerated nor retarded. And what will happen? So the diameter of the particle will affect the terminal settling velocity. So if it's a regular particle, spherical particle, the drag force, the amount of the drag force it will experience, that may be different if the particle is not spherical in nature. So then the concepts of equivalent diameter, weighted diameter, these concepts come into the picture. We don't have to go into that, but you can just visualize and feel the thing. If the particle is spherical, it is uh, settling very smoothly. If it is not, the geometry is not a very regular shape, it is not spherical, it will experience the resistance more. That's why the velocity with which it will settle, it will be as both of you have stated it correctly, Vasobraj and Prashant. So the velocity will be slower. So I think your answer is correct. Yes. So non-spherical particles is slower than the spherical particles. I hope why it is so. It is clear to others. Now the uh, next question. The peak factor is given by option A, peak flow into average flow, option B, peak flow minus average flow, option C, peak flow plus average flow, and option D, peak flow divided by average flow. You can type your answer in the chat box. I'll give you 2 minutes. Uh, yes, question is telling us the generally factors are stated as the ratio only. Sometimes also there are other mathematical operations like plus minus are also there. Generally it is, yes, it is generally it is true, but whether in this case also the factor is the ratio between that those two or not, that we will see. What about others? Prashant, Bashok, they have told us the Orchona and Krishna. Prashant is not responding. Oh, Orchona has left. Kavin Kumar. You can also answer. Don't be shy. I may be wrong also in certain cases, and some of you are even more educated than me. I am just a PhD student. Some of you, I just discussed with some people's background in my first session. So I came to know that some people have completed their PhD and they are in a faculty position in some institutes. So I mean, so it will be easier for you to answer those questions. Also, came back. Okay, so I'll the answer of this question. So all of you have stated it correctly. It is peak flow divided by average flow. This is how the peak factor is given. So I just told you the factor is generally the thing that is generally expressed as a ratio. So we will see this concept later in some other problem, solving some other problem. We'll see. Let's continue. So for a given discharge, the efficiency of the sedimentation tank can be increased by. This is an MCQ, and options are option A, increasing the depth of the tank, option B, decreasing the depth of the tank, option C, increasing the surface area of the tank, and option D is decreasing the surface area of the tank. So how the efficiency of a sedimentation tank can be increased? Please write your answer in the chat box. Sedimentation tank basically your works on the principle of the terminal settling velocity that I told you earlier. So sediments means those uh, those particles in the water which are not colloidal, not dissolved. They, if you keep the tank over a long time, the water stagnant, they will just settle at the bottom of the tank. That's all. So the concept, that concept is just you have to apply. So I would okay. So let people answer. Basubraju has told us A. Any other guesses? I'll tell you the answer. I also forgot it. What is it? Anyone else? Please come forward. I mean, type your answer in the chat box. Nobody is showing the courage. So the answer is increasing the surface area of the tank. So I'll tell you because I also got confused. Why is it so? With the depth, because it is a kind of terminal settling velocity, and the thing is that here efficiency means the amount of the particle that is getting separated. Okay. So the amount of the particle, that is basically your, not the time or anything else. Here efficiency means, if let's say a water is coming in, it has got a concentration of 50 milligram per liter, let's say, the sediment that is present inside the water, and after it is coming out of the tank, if let's say there are two sedimentation tank, one sedimentation tank is for the same feed inlet, one sedimentation tank is giving you uh, 25 milligram per liter, and another sedimentation tank is giving you, let's say, 20 milligram per liter of of sediment concentration at the outlet water. So the amount of the particle that is being separated, that is basically defined as the efficiency here. Okay, for the same rate, same flow rate. So that's why the surface area is important here. So that the efficiency, what do you mean by efficiency here? So to if you know this concept, then the answer will be, it will be easier for you to understand why it is surface area. But I also got confused why initially, because I didn't understand the concept of efficiency, or why what is meant by efficiency here. So that's why actually basically the surface area of the tank is the answer. Increasing the depth of the tank doesn't increase the amount of the particle that is separated. The rate of the particle separation, the depth doesn't increase. That's why basically it is the correct answer. So it's a very common thing to get confused. So no, as you will make mistakes. So that's why we'll be able to discuss these things forward, and others, if the people, if they are thinking that some thinking you as the same answer, so they may be having the same doubt. So if you go ahead and give the answer, then only you will be able, why we will be able to discuss that why it is a common mistake. So I'll encourage, that's why, to everyone to give your answer and ask doubt and be interactive in this session, because this is the idea of the live sessions, right? So otherwise you can always watch the session later, the recording later also. All the recordings will be provided. Okay. So everybody is clear now. Let's go to the next. Now some few problems and MCQs we will discuss on the grid chamber. So it is nothing basically nothing the same. The concept is basically same. The grids grids are basically nothing but the particles which are not visible. Again, the particle size is different. The sediment, the grid, all these things are basically defined by the particle size. So all these things are your grids and sediments. All they are not visible in the water. They are not colloid. If you keep the water stagnant, they will settle. The same concept here. So inlet water will come, and here is a concept. Sometimes an optional airflow is given. Why? If fats, oils, and grease, this cannot be separated in the grid chamber generally. So if they are present, they will just float. That's why. Then the after separating the grid, there will be a your after a certain amount of grit is stored, there will be a gate that will be opened. It will be taken out, and the outlet fresh water that will go out. This is the concept of the grid chamber. Very simple. Then you have a problem on the grid chamber. So for a grid chamber, given a flow velocity of 0.45 meter per second and a detention period of 45 seconds, calculate the length of the tank. Grid chamber is where the length of the tank in meter is important, right? In some cases, the length is important. In some cases, the surface area of the chamber is important, depending on the particle sizes. But the main principle here, is the same, because if you keep it for long, or if you The detention period means what? It is nothing but your HRT only. So if you keep it for in the tank, from problem solving point of view, it is HRT, but not from other point of view, technical point of view. So if you keep that thing in longer for in a stagnant situation, that will your settle, that particularly settle. If you just see the tank, you will see one thing, that again I'll repeat the concept of HRT that I told in last class. So the water that is coming in, all the particles, it is not like that all the particles of the water that is coming in, it will stay for 45 seconds in the tank. No, some particle will come like this and go like this immediately. Some particles will come like this, roam here and there, here and there, here and there for a long time. Maybe they may fall in the dead zone for a long time, and then they will go out, right? So if you plot a graph, if you just if you take all the water particles, so how the experiment is done, it is called as a tracer experiment. So some tracer element, maybe radioactive elements is given here as a pulse, and the output pulse is measured. So the output pulse you get, if you plot it versus time, you will get a Gaussian curve. Gaussian curve is a curve which is just like a reverse bell shape. Okay. So at a particular time, uh, you will get a highest number of tracer elements that is coming out. Tracer means what? Water particles you cannot trace separately. So that's why you just give tracer elements just like radioactive elements to measure the maximum amount of particles that is coming at what time. So the radioactivity versus time, this plot you get, and you get the Gaussian curve. The highest number of population, that gives you the corresponding times is your retention time. This is how it is. The experiment is done for any tank in a practical scenario where, let's say, the design data which the vendor has given to the plant, it has been lost. Let's say it is a nuclear power plant. How they will test? Let's say there is a jacket. So you want to know the retention time of water in the jacket. So they will put normal water, that is H2O. They will put heavy water, D2O, as a tracer or pulse. D2O means your deuterium. I know heavy water. I think you know that. And they will measure the output radioactivity, and they will plot radioactivity versus time. The highest amount of radioactivity they will get at a certain time, that will be your retention time. This is how they they assume that they are mimicking the rest of the majority of the fluid, let's say water, normal water that is present inside the water. In this way the retention time basically is calculated, but basically it represents, it is how it is calculated, but sometimes there is a something called as plus minus 2 3, let's say, like that way. They take a range instead of taking a point. But here this you just, for solving the problem, it's a very simple problem. You have to consider it as the space time. Okay. I mean, here the length is, you have been asked the length, so that's why it is just like your the velocity. So, I mean, the length of the, if the volume is the design parameter, then space time is uh, the I mean, tau is, T naught is your space time. The HRT is basically space time. Here the design parameter is length of the tank. Here the volume is not the design parameter. So same, you can understand. So that's why the flow velocity is flow velocity, not the volumetric flow rate, is related with the retention period. Please go ahead and calculate. It is I mean, not a very complicated one. Very simple. But the point, I mean, this is just a the I mean, multiplication and division problem. But the problem maybe get complicated. There are certain there are expectation factors in statistics. There are complicated things. So those things basically are done. You may imagine that why so fast about it. Why I mean telling so many things for this simple problem. So because this problem is basically from a complicated aspect, complicated scenario, it is very much simplified and it is given. Just for your understanding or knowing, I'm just discussing. Uh, but for the exam perspective and for the assignment perspective, only simple problem will be given. Uh, no worry about that. So I think what I told it is clear to you. And anyways, if you don't understand also, I mean, you don't need to understand. I mean, you don't have to get afraid about that. Just solve this problem. That's all. Which will be given in the exam. Okay, so very simple problem. The length of the tank is you have been asked. So the solution is flow velocity is given 0.45 meter per second. Retention time is 45 meter per 45 second. So length is nothing but your flow velocity into detention time. You just see the dimensions. That's all. Meter per second is second. Second goes out and is meter. So 0.45 meter per second into 45 second, it becomes 20.25 meter. All right. Okay. Uh, Now you have to select the correct statements regarding grid removal. It is an MSQ, that is multiple select question. Option may be one or more. Okay. So MSQ may be an MCQ also. There is no guarantee. Option A is you have to select the correct statement. Option A is in aerated grid chambers, there are zero moving parts below the water surface. Option B is grid chamber is usually installed after primary sedimentation tank. Okay. Option C is grid chambers are used to remove oil and grease from wastewater. Option D, the purpose of the proportional weir at the end of the channel type grid removal system is to measure the rate of flow inside the channel. We just welcome Indubala. Indubala. Uh, you just have to give the option for the correct statement. I mean, it may be more than one also. We saw earlier that option C, that is grid chambers are used to remove oil and grease from the wastewater. Is it true? Mm, I don't remember, but I don't think so because we saw in the picture they are floating, right? Grid may be the waste that is collected as grid that may be used for certain other purposes. If oil and grit is present in that grid, it may cause problems. So that's why if that causes problem, then uh, uh, compressed air will be used for the flotation of the oil and grease. If they don't cause problem, the air flotation will not be installed because it requires additional amount of energy, right? So that's why it was written in the picture as optional. In the bracket, the airflow was written as optional. But anyways, grid chamber is not designed for the removal of oil and gas. It may remove by chance, but it is not used for that purpose. I think option C is not correct. Let's see. within option A, B, and D. What are your responses? Only Prashant has shown the courage to give the answer. Option D is correct. You are saying. I also think it is true. Is there any other correct option? Any other is thinking about what about option A and B? Is there any uh, correct statement among them? Orchona, Indubala, and Kevin. What about you? And also Iduki, MISDSM Iduki. So, what do you all think about the other options? Are there any correct statement, or the others are false? Only D is correct. Hmm? Okay, so we will see. Uh, okay, so option A and D are correct, right? Because grid chamber separates the uh, particles which are not miscible, not dissolved, not suspended. They are separating those kinds of particles, right? So they are installed at a very preliminary stage. They are not installed after the primary sedimentation tank. So grid chamber is grid means larger particles than the sediments. So both are not miscible, completely miscible in the water. That's why by the help of gravity they are settling, gravity or the terminal setting velocity or other concepts. So they both of them are not visible, but the particle size of grid are more than the sedimentations. So as you go from the upstream side to the downstream side in any of the wastewater treatment plant, the particle size, those are getting separated in the different unit operations in that plant. They will basically decrease in size. So the larger particles, they are separated at the upstream, that is your preliminary, primary, grid chamber, sedimentation tanks like this way, and the smaller size of particles, though they just like the dissolved zone, they are separated at the latter stages, just like your bivalent salt, they are separated in nanofiltration, monovalent salts, they are separated in RO. So the finer particle, the more you go from the upstream to the downstream side of any wastewater treatment plant, the particle size, those are being separated, they decrease. Okay, so option B is obviously incorrect. Option C, I told earlier, it is incorrect, and option D is correct. And option A, in aerated grid chambers, there are zero moving parts below the water surface. So what did you see in the picture? If you see in the picture, so if you see the consider this as the water surface, there is zero moving parts. Obviously, there is air flotation, the air is obviously it is moving, but it is not a part of the equipment, right? It is a fluid. So the pipe which is blowing the air into the water, that is fixed. The entire thing is fixed. Moving means here continuously moving. I think you have given it as, nobody has given it as correct answer, is because you may have thought that the grid gate that is being opened after a few interval for the collection of the grid that is present at the bottom of the tank, so that is moving, you may have thought, right? That's why you have considered it option uh, what is the option A to be incorrect, you may have thought, that's why. So yes, so there is a discrepancy, you may say. So in reality there are zero moving parts, zero continuously moving part. Zero moving parts here essentially means zero continuously moving parts below the water surface. So the gate is obviously moving, but it is moving not continuously. It is moving at a very less frequent interval when the chamber is being filled at the bottom. and then the water supply obviously then it is cut off and the grids are taken. Otherwise, the water that is taken, so it's a kind of batch thing. So it's just like cleaning up your water filter. It is in your in continuous operation. But while you will say there is a moving part in your aquaguard, no, right? But when the service persons come in your house and they clean the water filter, they obviously uh, use the I mean, they obviously opens it, then it's actually moves, but that doesn't count. So zero moving parts means essentially continuous moving parts. So that's why, along with option B, option A is also correct. Okay, I hope it is clear. Nobody has any objection, I guess. Then again, then we will. Okay. So next question we will start after taking six or 7 minutes break. Okay. So we'll again rejoin in the same link around 8 before 8:10. So we'll start at sharp 8:10. Okay, we'll take a short bio break, and during the time, if you have any, I am here. So if you have any doubt on whatever we have discussed till now, you can ask, unmute yourself and ask. Okay, so next portion will be mainly based on BOD, biological oxygen demand. So we will see the concept of BOD. We'll solve a couple of problems on that. Yes, that's what I can remember. So whatever discussed till now. So if you are having any comments on that or anything, you can just express your thoughts. Or even if you are having any greater industrial experience and you are just doing this course as a part of your corporate program for increasing training credentials or academic credentials or whatever, then you can also share your industrial experience on whatever the equipment we have discussed till now. That will also be a greatly beneficial to the other learners who are just who don't have any industrial experience. They are just starting their educational career, so you can just share your experience also. That will be beneficial for them. So I encourage you to do that if you are having the same on any conceptual things also. If you have seen such and such design thing in during your bachelor's industrial training in the BTech program, there are in the final year there are bachelor training programs. So some colleges have, I mean, in some colleges, in most of the engineering colleges, basically you have to mandatorily do this industrial training. If somebody has visited any water treatment plant before, they can share their experience with the audience. That will be of great help. Otherwise, restart the same. We'll join the same link uh, within 5 minutes. Okay, so we'll start at sharp 8:10. Okay, so we are back. Uh, Only three people are back. Where are the others? Don't know. We'll start. They will join in the middle. Okay. So in the next problem, you have to select the incorrect statements regarding screens and their purpose in wastewater treatment. This is again an MSQ, that is multiple select questions, and the options are option A: screens prevent any interface to treatment. B, screens are used to protect process equipment. C, screens are a part of secondary treatment. Option D, there is no head loss when sewage flows through them. Bashobraju, Orchona, and Indubala. Any one of you? What is the your which one or two among, or three or all of them among the following are incorrect statements? Bashobraju is saying C. Second, screens are a part of secondary treatment. Obviously, bar screens, fine screens, all of them are not a. I mean, they are a part of preliminary treatment. Even if before the primary treatment, they are installed to separate the full patte bakara or whatever, the larger particles. Screens means that only the party to separate those particles which are visible to the naked eye. They can never be a part of the secondary treatment, right? This is a wrong statement. And any other statement, Archana is all are feeling option C to be wrong, or Bashobraj is also feeling option A. Screens preventing any interface to treatment. Okay. Option B is basically I think it is correct. Screens are used to protect process equipment. Yes, because if those particles goes into the process equipments, that they will damage. Let's say there is a pump that is pumping the sewage in a secondary treatment tank from or out, in or out of a secondary treatment plant. What will happen if particles present? So it will damage the impeller of the pump. So before most of the pumps, you will see in any plant there will be a pocket pocket kind of thing. In a there you will see a cylinder. This cylindrical pocket uh, in the suction line of any pump, it is nothing but a filter which separates out any, if by chance if the screen somehow fails, if by chance there is or even if the screen is working fine, there is a certain open area in the along the treatment, let's say. So some particles may fall from the air, right? So those particles may, if they are large enough, they can damage the impeller. So that's why those screens are installed to separate the coarse particles. After certain times, those screens, there are screws at the top of those filters. They will be opened, and that filter will be taken out and will be cleaned like that, or they may be cleaned by backward also. It depends on the manufacturer and the design how it is done. So, in a preliminary system, obviously the screens are installed to protect the equipment. Hmm. So option A and C, I think you are saying it correct. Let's say, what is the answer? So the thing is that option C and D is the incorrect statements. Okay. B is, I told you, it is correct statement. C is incorrect. It is also common. Why D is incorrect? There is no head loss when sewage flows through them. So I think you should have told it. Nobody has given answer as D. So why? Because in any kind of equipment, if the fluid be it sewage or any kind of, it may be gas or it may be liquid, whatever. If any kinds of fluid flows through any kinds of equipment, there will be a certain head loss. It may be very small, negligible, it may be high. Why negligible? If the fluid is flowing and there is wall friction inside that equipment, inside the pipes, there, due to that wall friction, there will be head loss. The head loss is lesser in amount. If there is, you say, if along the flow path, if the fluid experience an obstruction that is 90 degree with the direction of the flow, then maximum amount of head loss occur. So in screens, those screens are placed basically in 90-degree position, or maybe in a slightly slanted, but it is more than 45 degree always along the direction of the flow path. So that's why, or there will always be uh, head loss if the any kind of fluid, be it sewage or whatever else, if it flows through them, these screens, there will be certainly head loss. So that's why option D, that there is no head loss, it is an incorrect statement. Option C is also incorrect statement, and option A and B are correct. Okay. Screens obviously does, it doesn't. I mean, it your uh, prevent any interface to treatment, right? Okay. Within screens, no treatment basically occurs. It separates. There is no reduction in BOD and COD, etc. So only it is a separating device. So it prevents any interface to treatment. Now it is clear. We will go to the next next MSQ. So you have to select the biodegradable organic matters from the following. Option A is carbohydrates, option B is methanol, option C is fats, and option D is polyethylene. Obviously, nowadays you will see there are certain biological innovations with which, even if in this problem you see certain are not biodegradable, you will see research papers on those compounds. You will see there are certain bacteria or certain methodologies are being developed day after day, which are able to degrade even that also. Hmm. So there are innovations kind of thing. So in that sense, all of the four are your biodegradable. But what we are talking here, it is standard industrial practice. So in standard continuous process for equipments, which kinds of the uh, compounds can be biodegraded and cannot be biodegraded. That is only you have to consider here. Hmm. And you have to give your answer based on that. Archana is saying A and C. Basubraju, it is your earlier answer. A and C, carbohydrates and fats. I think it is correct, quite common. We don't have to worry much regarding carbohydrates and fats. They are biodegradable. Carbohydrates, proteins, fats, these three are basic biomolecules which are present inside our body. The methanol, it is a very toxic compound. It cannot be present inside the water. Even if ethanol, it is not also generated in our body. It is generated by some industrial processes. So ethanol also is not, though it is used for consumption, but it is not good. That good for it causes liver cirrhosis also. So alcohol as a whole is not that biodegradable. if the carbon chain is shorter, like methanol, ethanol, etc. But if the carbon chain is longer, it gradually becomes biodegradable in industrial process. But obviously, nowadays several innovations are there which can degrade even shorter length alcohols. And polythene is basically plastic. So people are trying to polyethylene means polythene, same thing. So people are trying to biodegrade it. There are certain microorganisms which can degrade plastic. You'll see such and such reports in research journals and all, but those are not yet commercially available. Otherwise, government would not ban the use of plastic, right? So plastic and methanol as a whole, they are not generally biodegradable, and carbohydrates, fats, proteins, these are all biodegradable compounds. Carbohydrate are basically used in industrial processes to produce the alcohol. And fats, I don't know. Can anyone of you give any example of any industrial process where fat is biodegraded to produce any other byproduct or so? It will be beneficial. No example is coming in my mind. Okay. So next question. It is a problem. Is it a problem? No, it is an MCQ. So a wastewater stream is mixed with a river nearby. After mixing, formation of certain zones occur. Which one of the following zones is characterized by the highest level of treatment of pollutants? So option A is zone of degradation, option B is zone of recovery, option C is zone of clear water, option D is zone of active decomposition. So if you see the river is flowing and you are looking at the river from side, then the wastewater stream is mixed at the river at certain point, and after the wastewater stream is mixed and along with the region where the wastewater is not mixed also, the entire region that is distributed along the length of the flow of the river, or which is the parallel to the direction of the flow of the river, the zones, the regions are divided into several certain zones. Okay, so which one of the following zones is characterized by the highest level of treatment of pollutants? So this is not your artificial treatment. So there are naturally microorganisms, microbes that is present inside the river and that is flowing through the river water, and they starts treating the uh, the micropollutants or micronutrients that is present inside the wastewater stream. In which zone they show their highest activity? The natural microbes, those are present inside the river water. In which zone they show their highest activity? That is the question, right? So anyone? Any doubt regarding any previous question or any doubt regarding this question? You can ask. This question after obviously giving the answer. How many of you have joined? Or Shruti Kodam. You can go ahead. So you joined after the break. Can you give the answer? Type in the chat box. Okay, option D. Okay. So I think you have given it the correct answer. So okay, I just told you. So there are basically zone A, zone B, zone C, zone D, and zone. There are 5 zones. These zones are divided based on the DO, that is dissolved oxygen, that is present inside the water. The entire zone is considered as the zone of pollution. Okay. Now, the name of the 5 zones are respectively clear water zone, the zone of degradation, the zone of active decomposition, the zone of recovery, and the zone of clear water. This is your average DO, that is 40%. It is your average dissolved oxygen. So zone of clear water that is the ekdam initial or starting zone, and the last zone, that is your zone of clear water. These two zones, they are having the highest amount of DO. Okay, and the zone of degradation and zone of recovery, there are falling rate and increasing rate of DO, and in the zone of active decomposition, there is the lowest level of dissolved oxygen, and it is constant. It is not falling or increasing. Okay, so why is it so? Why this kind of graph you see, that you will see. So basically, these are the 5 zones. So zone of clear water, these are zone of clear water. This is the zone of active decomposition, the third zone, and the second and fourth zones are the zone of respectively zone of degradation and the zone of recovery. Zone of recovery of what? Zone of recovery of dissolved oxygen. Zone of degradation of what? Zone of degradation of dissolved oxygen. So dissolved oxygen is degrading, dissolved oxygen is recovering in these two zones. Okay. And if you see, though the entire zone is called as a zone of pollution because certain buffer is taken, the wastewater is not introduced at this point. The wastewater is introduced at between the zone 1 and zone 2. So immediately after the wastewater is introduced, the dissolved oxygen's level basically your falls down. It is minimum at the zone of your active decomposition, then it is again increasing. If you see the number of species that is present inside the water, number of species means you see there are various type of microbials. That is your A, B, C, D, E. Let's say there are let's say 20 types of micronutrients, 20 types of microbes that is present inside the water. But the wastewater that is getting discharged, there is a specific type of pollutant that is present inside the water. So listen carefully here. So let's say 20 types of different species, only 5 among them, let's say, they take the micropollutants that is present inside the water as their food. The other type of species that is present inside the water, they don't they don't eat the organic pollutants. Okay, so only those 5 of species, they will start eating the food, and the other types of species, their number will decrease. You see the other types of species, they will gradually die, right? So the total number of species, they will decrease, but the population of individuals in those species, that is your 5 species, they will increase. So do you understand why it is so? So specific types of your microbes which are which will eat those specific types of pollutants that is present inside the water, they will thrive, but the other kinds of species, they will die. So that's why there are two opposing effects you can see here. But after the that is called your uh, what is called your after the active decomposition takes place, then there is no micronutrients present inside the wastewater. So you can see this is the direction from left to right. It is the direction of the flow of the river. So river water is flowing in this left to right. So it is distance downstream. Okay, and after the recovery phase, after the dissolved oxygen, how the dissolved oxygen comes in the water? So river water, there is turbulence. So because of the turbulence, there is continuous mixing of air inside the continuous mixing of oxygen from air inside the water. Okay, and there is also microbes which are degrading those pollutants and utilizing the oxygen. So in this region, they are utilizing the oxygen in highest number. So that's why the rate of their consumption of oxygen is more than the rate of mixing of oxygen from the air into the water. So if you remember the mass balance, you will understand why there is an overall decrease in the DO level. And after the recovery phase, the rate of consumption of oxygen by the microbes for the degradation of the micropollutants in the wastewater is decreasing. The rate is decreasing. So that's why the mixing rate is recovering the amount of dissolved oxygen that has been lost during the degradation process. So I hope the graph is clear to everyone why it is so, each and every point of it. Now you will be able to understand any type of question. Let's say the question is modified a bit. It has been modified like this way. So instead of highest level of treatment of pollutants, they just told that decreasing level of treatment of pollutants or increasing level of treatment of pollutants. So decreasing level of treatment of pollutants means increasing level of DO, and increasing level of treatment of pollutants means decreasing level of DO. So in this way, if this terminology is changed, you should be able to identify the zone, right? If you have understood the graph, or in terms of let's say DO, I mean, without telling the DO, let's say they told these things: species, populations, highest number of population of individuals in each species, let's say, or lowest level of DO. So then that will also be the zone of active decomposition. So in this way, you should be able to answer. So that is the idea. I hope it is clear to all of you. So the introduction of this concept through this MCQ was necessary for you to understand for you to understand the concept of BOD and solve the further problems. So the next MCQ is the measurement of biodegradable organic content is usually carried out in the terms of DO, BOD, COD, and TOC. So now we will introduce the concept. Please answer it. It is very simple, and we will solve certain problems based on this within the last half an hour. Okay. How the measurement of biodegradable organic content is done. What is the measurement of the biodegradable organic content? Is it DO? DO is the dissolved oxygen. BOD means biochemical or biological oxygen demand. COD means chemical oxygen demand. And TOC means total organic carbon. Okay. So Basobraju is telling as BOD. As we will solve problems on BOD, so we'll take this answer, and it is the correct answer, BOD. So we'll just tell what is your biological or biochemical. Some people say it biological, some people say it as biochemical oxygen demand. So what is it basically? So if you plot BOD versus time, then you will see there are two steps. In the first step, it is called as the carbonaceous stage, and the second stage is called the nitrogenous stage. The BOD level increases in this way with time. And if you see this graph, it is basically, it is not the treatment graph. It is treatment graph. If the BOD is kept inside a closed bottle, let's say it is a BOD incubator. The bottle is kept inside a BOD incubator. No further mixing from outside no mass transfer takes place through that bottle. It's a closed bottle. You will see there will be a gradual decrease of the BOD over time, and the gradual decrease is expressed with the help of this terminology. So BOD equals to L0 into 1 minus e to the power minus KT. This is your first order kinetics. If any one of you know how the BOD is measured physically, then you will understand the BOD bottle is nothing but a batch reactor. And the rate equation is nothing but these two equations are nothing but first order kinetics. These are not second order or zeroth order. Okay, these are based on first order kinetics. So that's why you will see a gradual decrease of the BOD over time. If you put T as 0, okay, then LT will be equals to L0 and BODT will be equals to LT equals to L0. That means this point is your L0. If T equals to 0, then LT is L0. Okay. So this formula you have to keep in mind. BOD is nothing but a first order batch reactor kinetics. This will be used for solving your problem. So what is BOD basically? BOD is difference between two dissolved oxygen. Let's say I told you T equals to 0. It is the initial BOD when you are if any let me explain first how BOD is tested. So if anyone of you know, you can come forward, elaborate, or I'll tell. So it is in simple terms, it is nothing. So there are experiments, there are titration methods with which you can, and there are also online meter. Those are not very perfect, but yes, they are also in use. They are in a state. Researchers are going on to perfect them. Hmm. So there are chemical methods for measuring the amount of oxygen that is present inside the water. There is one compound called as alkaline potassium pyroglycerate. It can absorb oxygen, right? We all studied it. So with the help of that, the amount of oxygen that will be evolved, that can be absorbed, and it can be indirectly measured. There are also other methods with which you can measure the dissolved oxygen that is present inside a certain amount of water at that particular time. Okay, so now let's say in this graph T equals to 5, so 5 days, then the difference between the dissolved oxygen at the day 1 and after the day 5, that difference is called as the BOD5. If the T equals to 3, then the difference between the BOD at the starting of day 1, that is day 0, and the day 3, that difference is called as the what? As the BOD3. In this way, you have to keep first the water sample, wastewater sample is taken from the river or whatever place you want to measure the BOD. That wastewater sample is taken, that is kept inside the bottle, that is kept inside the closed bottle. There are certain compounds is added, that those are dilution water, those are for the uh, so that the microbes can thrive. That's why, because there is a mixing from the outside, so that's why there are certain protocols are there. So basically they are just kept as it is inside a particular temperature. This is standard temperature, and the microbe, due to the microbial activity, the microbes consume the oxygen, they degrade the pollutants that is present inside the water. In this way, the dissolved oxygen, as they though they are mainly the aerobic bacteria, so biochemical oxygen demand. So oxygen, there is a demand of oxygen for what? For degrading the pollutants inside the water. So there is a decrease in the level of dissolved oxygen. So you are measuring the decrease over 5 days, or let's say 3 days. So this difference in DO indicates the, basically it's an indirect measure of the biodegradable pollutants that is present inside the water. So that is biodegradable how many days? Biodegradable for either 3 days or 5 days, depending on your problem. Okay. So conventionally, only 5 days BOD was there. Can any one of you say why BOD 5? I mean, we start solving problems with BOD 5. It was initially there, BOD 5. Later, BOD 3, 4, 7, other concepts came into the picture, but we still use in our laboratories. If somebody is doing experiments on BOD, they will be able to say that mostly we use 5 days BOD, and though that was earlier when the BOD came in, the concept of BOD came into the picture. Can anyone tell that why it was 5? BOD 5 initial. I mean, it was conventionally taken as t equals to 5. That time, these graphs and all these concepts, problems are now we can get the kinetics, the k value by taking BOD over several days. Let's say 1, 2, 3, 4, 5, 6. Like that way, we can plot a data and we can get the k value. So whether it is remaining constant, whether it is varying, how should we calculate? And we can calculate the BOD over any days. We can extrapolate the data, right? But initially, these concepts were not there. Initially, only people calculated the BOD 5. Can anyone, or anyone of you know that how the 5 thing came into the picture? Based on microbial growth behavior. Behavior, yes, that is true. Okay, I will tell. So why 5? There is a basic reason. Not many people know it. So when I was working in a particular industry, so the engineer of that industry was actually in charge of that effluent treatment plant. Actually, I came to know from him. Actually, I learned from him. So he told that the basically, the industrial revolution. It happened in your in the Manchester city, in Europe, basically, right? So there is a basically river. It is in England, right? So the Thames River is flowing. I don't remember. So at the side of that city, this river is flowing. So from the region from where the industries are situated in the river, the retention time for that water part for the from that region to the bank of the to where the river is mixing to the ocean, it is requires 5 days. So that time is 5 days retention time. If you recall the concept of retention, so that's why from that region they just viewed it like that way. So if you are, let's say, throwing this high amount of BOD. BOD means the demand. It is an indirect measure of the organic pollutants that I am throwing with the wastewater. So if I'm mixing it at this river point, and river is after 5 days, let's say, depending on the velocity of the river, on an average, after 5 days, it is going to the ocean and it is mixing. So within this time, whether it will be able to recover the dissolved oxygen that has been lost for the or whatever organism that is present inside the river, they will they be able to degrade that uh, pollutants that is present inside the water or not. So they initially started calculating based on BOD 5 only. So they just took the retention time and they just calculated BOD 5. BOD 5 means what? They just took the initial sample, measured the DO at the day 0, and they measured out, they kept it closed. After 5 days, they just measured the DO. And by the difference, they just used the BOD, biological oxygen demand. So these 5 days, they indirectly took that this is the your amount of the pollutants that will be treated within this time. So that's why they, in this way, the concept of BOD 5 came. It is not the basic. It has not the convention came like this way. Do you imagine? It is a BOD is a relative concept, so you can take up to any days. After certain days, it becomes your asymptomatic. So initial days there will be high amount of decrease in DO, right? So after that time, the decrease rate will gradually rate of decrease will gradually also decrease. So if you know the nature of any asymptotic graph, you will know. But why the concept of 5? It came into the picture like this way. So you can take any number. The more you take, the more it is accurate. So why 5? It is because of that. From there the concept came. It's kind of relative concept, BOD, because DO is an absolute concept, and BOD is never going to be zero, right? That dissolved oxygen that is present inside the water, that is never going to be zero. So that you cannot get the absolute amount of organic matter that is present inside the water that is biologically degradable. You cannot get. So it's a kind of relative concept. So it depends on the T, how much T you are taking. If you are taking 3 days, it will be BOD 3. If you are taking 5 days, it will be uh, giving you the 5. So I hope it's making sense to you. Okay. Okay, so we'll solve for we'll go further for solving. How much time is left? So 15 minutes left. Maybe we'll solve a couple of problems on BOD. So first problem is an industrial outfall is releasing 4.32 megaliters per day. That is 10 to the power 6 liters per day, effluent to a river having flow rate of 12 meter cube per second. The background BOD level in the river is 0. So this base level needs to be mentioned. And BOD in the wastewater is 12,050 milligram per liter. The permissible BOD limit in the river water is 10 milligram per liter. You have to assume instantaneous mixing at the discharge point. Then you have to calculate the BOD of the river water at the discharge point in milligram per liter whenever it is mixing. So in first problem, no rate kinetics, nothing you have to take. You just have to do a simple mass balance to get the net BOD of the water at the mixing point after the mixing takes place. So I will give you 2 minutes to solve. Take your copy and do this math. A1 B1 plus C1 D1 equals to E1 F1. Just like that, you have to solve mass balance, simple mass balance. I think so. No. You see the problem. What is there? If you don't understand the problem, then ask me. So the flow rate of river is 12 meter cube per second. The flow rate of the effluent is 4.32 megaliters per day. This you have to convert liter to meter cube conversion. I know everybody know. If you don't know, you can Google it. Megaliter means I have told 10 to the power 6 liters. Mega means M. Mega means basically million, nothing else. Million liters per day. Yes. So mega, million, all this means 10 to the power 6. Micro means 10 to the power minus 6. Giga means what? 10 to the power 9, right? Tera means 10 to the power 12. I don't know, maybe. So they basically increases with the order of 3 and decreases with the order of 3. 10 to the power minus 3 means milli. 10 to the minus 6 micro. 10 to the minus 6 nano. Sorry, 10 to the minus 9 nano. Minus 3 minus 6 minus 9. Similarly, 10 to the power 3 kilo. 10 to the power 6 million or mega. 10 to the power 9 giga. 10 to the power 12 maybe tera or something. But in this way, you just do. These are two flows. They're coming. They're mixing. The net flow rate will be nothing but the summation of these two flow rate. So 12 plus 4.32 converting to whatever else per day it is. So you have to convert it per second, or either you convert this one or you convert that one, whichever you like. So you convert any one unit to other unit. You just mix them two and get the net flow rate. Okay. And you also multiply these two with this two calculation. You multiply with this flow rate with this concentration and you add them up and divide the net with the net flow rate. You divide it, you will get the what? Get the BOD of the river water as is. I told you BOD is nothing to worry about. BOD is nothing but a concentration. It is an indirect measure of the concentration of what? Indirect measure of concentration of the biodegradable organic matter that is present, biodegradable organic pollutant that is present inside the wastewater. So the river water that is coming, it has got a 0. Okay. So your basically answer will be after unit conversion, it will basically 4.32 into 12,050 divided by your the total flow rate. That will be, that's all, because 0 into 12 meter cube per second. The river water that was initially flowing, it has having 0 BOD level. Anyone has come up with the solution? We have to go fast, otherwise we will not be able to solve the other problem. Maybe we will have to wait for the next session. So I will go with the solution for the sake of time. So solution data given is effluent flow rate is 4.32 mld equals to 4320 meter cube divided by 24 hours per day, because it is per day, into 3600 seconds per hour. So it became meter cube per second 0.05. Now effluent BOD is 12,050 milligram per liter. River flow rate is 12 meter cube per second. These are all the data given. Now it is also given that river water BOD is 0. Now BOD at the discharge point you have to calculate, right? Simple as I told. So river water is having 0, 12 into 0. And the effluent that is coming in, it is this 0.05 meter cube per second into the effluent BOD, that is 12,050. This is your, this milligram per liter is your, this many milligram per liter your total BOD divided by the total flow rate. If you consider it as a Y shape, one is you are coming in, another one is another arm of the Y is your effluent coming in, and another arm of the Y is your the total flow going out. So the total flow is your 0.5 meter per second divided by 12 plus 12 meter per second. If you divide this with this, you will get BOD as 50 milligram per liter. So here you can see there is meter cube per second and there is meter cube per second. This got cancelled out and milligram per liter was the answer. Nobody calculated it. I hope you have understood the concept. So acceptable, yes. So you have given an acceptable range between 45 and 50. Your answer will be correct. So now the second problem, they are asking the percentage BOD removal required for the industrial wastewater to ensure the BOD of the river water sustains within the permissible limit even at discharge point in percentage. So they are saying river water is coming at 0 BOD, 0 BOD, 12 meter per second. The industrial outlet is coming 4.32 mld at 12,000 milligram per liter. But this 10 milligram per liter, which is your permissible limit, we calculate it as 50 milligram per liter, right? So you have to bring that 50 milligram per liter down to 10 milligram per liter. So this 40 milligram per liter, you have to decrease BOD level, right? So for this reason, you have to mix dilution water. Dilution water means what? Water that is just like the fresh river like water, which is having 0 BOD. So this amount of water, either you have to bypass it from the initial before the mixing point, you just have to bypass it and mixing it with the industrial wastewater before throwing it out in the river, or you may take it from any other sources, other abundant sources, let's say rainwater harvesting, or by whatever means which is having 0 BOD. So this 0 BOD water, you have to dilute that water. Okay. So in this way, you can ensure the BOD of the river sustains within the 10 milligram per liter, even at the discharge point. Okay, so this problem you have to solve. So this is up to what we have solved. So we have not utilized the 10 milligram per liter, which is the permissible limit, till this point. So now that thing will be utilized. Can anyone calculate it for me? 2 minutes time I will give. Maybe 1 minute, because after this we will solve another problem. Nobody? Half of people left, I think. Only Archana, Indubala, and Basupraju are there. Are you calculating in your copies? So you don't have to take any notes. Just for the sake of problem solving, you can keep a scribble pad at your side, and pen you can just for the solving purpose. If you are doing more, I understand if you are doing more than one courses, these 2 hour session and also along with the lecture sessions may be a bit hectic for you. You can just, I mean, if it is not hectic, you go through it. But if it is hectic, you can watch the recording. No big thing about that. But yes, we'll encourage always to attend the live interactive session. And so we have designed the slides and the entire course content also such that you don't have to again sit with it again. So if you just go along with the session, that will be sufficient for your exam and solving the assignments. So you don't have to again recapitulate it and again sit. So the only the 2 hours time per week if you give and the course time. So you just go through it as it is going in the live sessions. It will be beneficial for you for your solving assignments and exams. You don't have to again sit with it. So even if you are not attending, then you have to watch the recording. If you are attending, these are designed in such a way it will I mean हिंदी में बोलते हैं ना हृदयंगम हो जाएगा. So it will be your in your soul like that in your spirit. So you don't have to remember. So these are designed in such a way. So it's very thoroughly and very basic way these are discussed. Okay. So I'll only 3 minutes are left. I'll go with the solution. So maximum BOD in effluent to restrict the BOD at discharge point as 10 milligram per liter is 10 milligram per liter into 12 meter cube per second divided by 0.05 meter cube per second equals to 2410 milligram per liter. Okay. Hence, percentage treatment required is 12,050 milligram per liter minus 2,410 milligram per liter divided by 12050 milligram per liter goes to 80%. So how much BOD you have to remove? This is the total BOD. Do you understand? So how you are getting this percentage? So this 10 milligram per liter is your restricted up to this BOD level. You can only keep the BOD, right? And this is your which flow rate? It is your river water flow rate. After addition, so this 0.505 is your effluent flow rate. This is the river water flow rate. Total flow rate is 1205. The total flow rate you have to keep this BOD. So if you multiply them, whatever you get, that you have to keep that BOD. You have to keep within this effluent flow rate. So before throwing it out, you must bring down the BOD of the of this effluent up to this level, 2410 milligram per liter. Now, what was the initial BOD of this thing? 12,050, and you are bringing down up to this level divided by 12,050 milligram per liter. 80% treatment of BOD treatment is required. So, if the flow rate, if it let's say dilution water, you are told that you have to add the dilution water, then you have to add based on this percentage. Okay, so that equivalent reduction of BOD occurs, and this 10 milligram per liter outlet, this 10 milligram per liter of permissible limit of BOD at the discharge point is maintained. So in this way, the answer of the second problem is 80%, and this one is 50 milligram per liter. I hope it is clear to you. Now acceptable range is again for this is 75 to 85. If you have got your answer between these two, then it is correct. Now, is there any? I don't think there is any other time. So if you have any questions, the other slides will be maybe one or two problems are there based on BOD. It will take 10 minutes or so. We will discuss this in the next session. So whichever was discussed until now, till now, if you have any doubt, you can ask regarding this problem. What was asked, how was it, how it was solved, regarding the concept of BOD also. Okay, and actually, in this problem, there was nothing related to kinetics, right? In the next problem, there will be there will be the concept of BOD kinetics, which will be there. The first order batch reaction kinetics will be there. Okay, or in case of continuous flow, it will be T naught. You all know that. Okay, so this is why before the discussion of the BOD, the concept of the reaction kinetics was introduced. This is the reason. This is the logical flow of the order through which you should study. Okay. Okay. So if anybody has any question, you can ask. Otherwise, we will close the session within a minute, and we will meet in the next session next week. Okay. And the all these slides and recordings will be uploaded. Any doubt on this? You can ask. Regarding the mixing zones and all. Okay, whichever was discussed in this session. If you don't have any doubt, we'll close this session. Okay, fine. So meet you in the next class. Goodbye, everyone. Good night. I'll end the call.